Hi there, and welcome to the AbsInt videocast for the October release in 2021. My name is Christian Humbert, and I'm going to present the latest features of our binary level analyzers StackAnalyzer, aiT WCT Analyzer, TimeWeaver, TimingProfiler, and the ValueAnalyzer add-on. Let me start with an important note for our Windows users. The new release 2110 now requires at least Windows 10. Older Windows versions will no longer be supported. Now, let's get started with an overview about the new features in this release. As usual, I'd like to start with the improvements in the graphic user interface, followed by some improvements of the internal analyzer components, like the ValueAnalyzer, which is a central part of basically any binary level analyzers. Then we have some improvement in the cache and pipeline analysis of aiT in TimeWeaver. And last, I'd like to show you some new ARS2 specifications. All right, let's get started with the graphic user interface. The new release brings support for the DSpace target link version 5 and 5.1, and especially if you want to perform worst-case execution time analysis of target link model code. Using the AbsInt toolbox for target link can reduce the manual annotation effort a lot, since it will automatically generate loop-bound specifications for the auto-generated loops. Next is we have improved the graphic user interface performance drastically, and especially for projects with many analysis items. So if you have a project with hundreds of analysis items, this will be loaded and stored much faster than before. We have also improved the XML result file process, and I'd like to show you that in a small demo. I have here a project with 6 analysis items, and I have defined an XML result file here. If I open the file, I see the results from the previous analysis run. Now, if I restart the analysis of all enabled items, you see that the result file is now incrementally written after completing each analysis. This was not the case in previous analyzer versions. It was written at the very end, and if something went wrong in one of the intermediate analysis, you might have lost the entire XML result file process. So this has been improved. Specific improvements, I switch to ACube for TriCore here. The first new setting I'd like to show you is found on the setup hardware. Here you can provide the value of the PSWIO bit at the analysis entry, and the possible values are unknown if you don't know the content of that bit. 0, that means you are operating in user 0 mode, user 1 mode, or 2 in the supervisor mode. And the interesting thing about that is that some real-time operating systems use that PSWIO flag to determine whether it needs to perform a syscall first before calling the kernel APIs. And so that means if you know the initial value, 0, 1, or 2, this might improve the precision of your analysis. Let's stay in the setup hardware view for a moment. The next new feature, namely, is related to the given base address of the interrupt vector table register here. If you provide that, then there is a new ACE programs point specification available, which you can use either in the AIS files as wherever you need to provide a program point, or also as an entry to the analysis. The parameter of that interrupt entry operator is the pending interrupt priority number. And I'd like to show you what that brings as an advantage. So assume you want to analyze the interrupt level 1 here. Previously, you had to provide the analysis start address of the interrupt vector plus the offset for level 1, which would be 8 in this case. And well, then you could analyze that interrupt. Okay. Now that we've provided the branch interrupt vector table base address, we can simply use the new program entry, which is called interrupt entry, and the 0x1 for the pending interrupt priority level 1. So if I analyze that one, then I should receive the very same code. Yeah, and yes, of course, this can be done for every interrupt. Here, this is the level 2 interrupt, and the new program point would look like this. Let's come to the value analysis improvements. We can now set an active context from within the context-sensitive statistics view to use later in the interactive value analysis exploration. Let me show you that. So if we analyze the 10 millisecond task interactively and open the statistics, and we go to the context-sensitive WCET contributions and see, for instance, that we have string copy X that is called several times, and we would like to investigate on that specific context here where the string copy X is called at address 7F4. Now we can show this context in the call graph and set the active context for the interactive exploration. So let's do that. It jumps directly to the graph, but has set the active context in the background, so that if we open the interactive value analysis exploration now, we are immediately at the given active context, you see, where we called string copy X out of address 7F4. The October release introduces an entirely new domain in the value analysis, the so-called type domain. The rule of thumb is the more domains are active in the value analysis, the more precise your analysis result will be. This type domain now propagates information about types of variables analyzed in the program. So for memory cells and registers, the analyzer now tries to determine its types at every program point. Let me show you the effects of this new domain. So let's stay in our 10 millisecond task analysis. I'd like to repeat the analysis and switch to the report file first. In the report file, in memory access statistics section, you will find an overview about all load and write accesses by each function. And now you will find new informations about the types. For instance, here, this type info is new in this release, and it will propagate the information about the types of the variables. So even if you do not know the variable itself, you might have a benefit of knowing the type info, and this might help to resolve, for instance, more computed calls. You also see an effect of this new type domain in the interactive data flow exploration view. So for that, we could probably copy that address here and jump to the analysis graph, search for the instruction, and load the interactive value analysis results here. Because then you have here an overview about all domains, the register domain, memory cell domain, the relational register, relational memory, and so on. Now we will also find a registers type domain here. So the analyzer knows that in register R0 there is a variable. It need not to know which exactly, but it comes with a record pointer type, and the same in register R2. So you also have an overview about variables with its types here. The next affects the cache and pipeline analysis stages in the AIT worst case execution time analyzers only, and only those architectures which allow cache locking. Because the pipeline analysis now shows the total amount of locked code and data. Let me give you a short demo on that. Here in my 10 millisecond task, I have now specified that the entire .text section shall be locked into the instruction cache. And if I perform the analysis, under this given assumption, I now get a statistics about the total amount of cache locked code, namely 14 kilobytes. If I decide to additionally lock the data from the sections.data and read-only data into the data cache as well, we see that our statistics is extended. Now I see also the total amount of locked data, which is 775 bytes here. I think that these two additional informations help to verify that you do not exceed the size of the cache which you effectively can lock. Our hybrid worst-case execution time analyzer TimeWeaver also has been expanded. There is a new support for the ARM ULINKpro trace format, and we introduce a new trace process ID mask attribute to decode the process ID from a 64-bit address, for instance. Of course, if the thread or process identifiers are explicitly be contained in the trace data, there is no annotation required. Also, if the ID is stored into a variable or memory cell, it can be accessed by the well-known attribute running task. But some debuggers encode the thread or process identifier into the instruction addresses. In that case, you can use the new attribute trace process ID mask to tell the analyzer where the process ID can be found in the instruction address and to decode the identifier correctly. Here's an update on our ASCII specification language in the October release. I'd like to go through each of the new changes, and we'll start with the global attributes. You might remember from the last release in April that we've introduced new predefined global attributes for accessing the architecture, the analysis ID, the analysis type, the analysis configuration, and the analysis group inside of the by some annotations. And you access it with the attribute and then the name of it, and check it against some value. In this release, we extend the global attributes by the target type attribute. So you can now also access the target type of the current analysis. In this example, I'd like to apply a not analyzed and infeasible annotation for the fmul and fdiff functions only in the case if we are running a TriCore analysis and only if our target type, the target processor, is a TC377. This can be scoped now with this new target type attribute. The next is you can apply value annotations now to calls from a routine to another. So basically to the call edges instead to a program point to some instruction in a routine. This is especially helpful in case that the value annotation depends on some calling context. Here's some small example. Assume that you would like to analyze memcopy in the context where you come from handle input with some defined width of 80, while for all calls from handle output to memcopy, you would like to consider the width variable having a value of 40. So this time you can really put or attach the value annotation to any call edge between two functions. The new release version accepts more symbolic expressions in annotations, basically wherever standard symbols are used. Let's have a look to the examples here. Assume you want to make some function, namely the handle1 function, infeasible, but only in the case you are doing a stack analysis. If you do an aiT, worst case execution time analysis, instead you would like to turn handle2 into infeasible. This can now be expressed by this compact annotation where you have a symbolic expression here as a symbol, because it evaluates to handle1 if you are doing a stack analysis, and it evaluates to handle2 symbol if you perform any other type of analysis. The second example here defines a loop bound And here you switch on the analysis configuration, which is also symbolic. If you are doing an analysis of a task running on a core 0 configuration, you would like to apply 15 as an upper bound. For the core 1 configuration, a 10, and in the default case, just a 0. The new release introduces some new program point offset specifications. And the first one I'd like to present here is the wildcard offset. Before this release, if you wanted to annotate the first, second, or third computed call in some routine, you had to say, I'd like to annotate instruction R, computed 1, computed 2, and so on. Now we are introducing the star wildcard offset, which basically means that you go forward searching for all instructions that belong to the very same instruction class. So in this case, to the computed calls or branches. So in this example, I annotate all computed call or branches in R to be resolved by calling foo A and foo B. The next program point offset, which is new, is the assembly offset. You can also search for a specific assembly instruction. And again, the first, the second, or third assembly instruction which matches the given name. Of course, you can also use a regular expression to have a more generic pattern. And you can also use the wildcard offset here. That means in our example here, I'd like to search from the entry point of main to the fourth instruction, which is having the assembly string knob. And if I change it to star, I would affect or annotate all knobs in our main routine. The last new improvement is that we can now have nested instruction scopes in the annotations. So assume here this example, we would like to annotate the first return in main and the instruction right before the first return. Now you can combine that by introducing just one scope for the main return 1, and you say you annotate here the attributes for that, and you say instruction -1. From that instruction you can annotate some second attributes. This concludes the presentation of the latest features for the October release. Thank you very much for your interest. As usual, there is a complete list of changes that can be found on our website. Thank you very much for your interest. Take care and bye-bye.